Thank you. Right, so in my talk, I'm going to discuss algebraic topology. So, well, more generally, we'll talk a little bit about topology, a little bit about equality, equality in mathematics, that is. Homeomorphisms. So these are an important tool in topology to determine what spaces are different. And then we'll talk about the algebraic part, right? Because algebra turns out to be quite the tool for certain problems, right? And then I'll talk a little bit about homotopy towards the end. So what is topology, right? So topology is basically, it's the study of continuous transformations, right? From one space to another. So what we want to do is we want to figure out what properties of these objects remain constant as you over such transformations, right? So, you know, such as the number of holes, and there are many properties like these, right? And I think the most important, well, the key thing that we study in topology is something called the topological space. Now, this is the formal definition, right? So a topological space is just a space with a family of subsets that we'd like to call open. So if you've seen open sets before, like you know, from A level, there's the open interval and stuff like that, which you know, they're intervals that are bounded but don't contain the bounds, for an example. But you know, we're trying to here, we're generalizing things slightly, and we're trying to say, okay, what if we come up with a way to label sets as open, right? And yeah, there's many examples of this, right? So so here's a free donut for you, right? There's, you know, the torus, well, any surface that you can embed in 3D space, or, you know, 3D space itself is a topological space. Any metric space, the real line, and actually any set can be a topological space if you say, okay, I'm going to call all the power sets of the set to open. Yeah, that would satisfy these previous these axioms, right? Another one which you might notice is if we consider the set that contains the set itself and the empty set as our topology, then that also defines a topological space. So, you know, there are you can actually define multiple different topologies on different sets for sure. And they are what the most important thing about like the thing that we like to compare. So when I think of a topological space, typically I think of a region in space, or a surface, or a line, or something like that, right? But it could be more weird structures as well. So we tend to keep to that general form. Now, in maths, we do like to talk about equality, so equality of different things. So I mean, obviously, when we talk about numbers, we like to say, oh, when is x equal to this number, right? And stuff like that. But it's not so easy when we we have to be a bit more rigorous with how we define equality, right? And you know, a relation that we say has the qualities of equality, you know, is called an equivalence relation. And in fact, these are the axioms for an equivalence relation. So basically, they're reflexive, which means that if 1 equals 1, well, 1 is always equal to 1, right? So any element of the set is always equal to itself. If A and B is A equals B, then B equals A. And finally, transitivity, which is saying, look, if A equals B and B equals C, then A must equal C, you know. So yeah, that's that's kind of how we define equivalence. We can also define something called the equivalence class, right? Which is like saying, okay, we have the entire set of objects. Let's group them together by our definition of equality, right? So let's put them into like a little box here and say, okay, all of these things are equal, all of these things are equal, all of these things are equal, and nothing else is equal between the boxes, right? So for an example, let's give some examples of equivalence relations. So we've got numbers, of course. Numbers are just, well, we're modeling the equality of numbers, so it would be stupid if it didn't work, right? So birthday equality, right? So if I say I've got the same birthday as you, you also have the same birthday as me. I have my birthday is the same as my birthday, right? And if I have the same birthday as you and you have the same birthday as someone else, I also have the same birthday as that someone else. In this case, the equivalence classes, right, would be the days of the year, right? So we all put ourselves in these boxes saying this day is my year, my birthday. So everyone who has their birthday on that day kind of makes part of that box, right? One more thing, in probably in O-level maths, you've seen these like congruent triangles, and there's also similar triangles which have the same thing, right? So if two triangles are congruent, then well, if triangle A is congruent to triangle B, then B is to A, and so on and so forth. So these all satisfy these rules. Now, let's start with the actual topology. So homeomorphisms, right? So homeomorphisms are just functions between the two different topological spaces. So they have these specific properties, like F is bijective, so it's one-to-one and onto, right? It is continuous and has a continuous inverse. So for an example, if we go back here to this nice image here, we've got two topological spaces, right? We've got this donut and this mug. And you can see this transformation is continuous because there's no like jumps besides in the loop of the GIF, right? And every point is being mapped onto some other point. And it can go backwards, right, as well. So that's what we mean by homeomorphism. We can then define, an equivalence relation from this. So we can say that two topological spaces are homeomorphic if there's a homeomorphism between them, and we can, make that an equivalence relation, and we can prove all of these axioms in some sense. But in fact, most importantly, the symmetric property, right? If x is homeomorphic to y, then there's a function f that is continuous with continuous inverse that is bijective. Since it's bijective, it has an inverse, right? And that inverse function also then has these properties in these cases. So you do get this equivalence of classes. So that's why the famous joke of a mug and a donut are the same thing, right? Because we can put them into these equivalence classes under homeomorphism, right? So one neat example, which I like to look at, is let's consider the Latin alphabet, well, capital letters more specifically, right? So in the Latin alphabet, we can if we consider each letter as a topological space on its own, we can kind of see which ones are homeomorphic to each other. So let me annotate this. So for an example, we can see that the pen's not working. There we go. So we can see that here, for an example, these letters here, they have a hole, and they have like two legs, kind of. You can see that B is the only one that has two holes. All of these, in some way, you can stretch them out so that they're like a line, right? These two are the only ones that have a singular hole. These four, they're like three legs popping out from each other in some way. So this one's a bit like trickier to see. So we can like extend this line, and you have E like that. If you remove that, then you have one leg here, one leg here, and one leg here. And T is the same, right? And so is Y. Anyway, here we've got two lines and a line connecting them. So that's, two lines. Two lines and a line connecting them. Here we've got a circle and a single line coming out of it. And here we've got 4 lines. So these are kind of the equivalence classes of the alphabet under homeomorphism. So now let's get on to the main part of this talk, right? Algebraic topology. So, there's an important word there, algebra, right? And it turns out it becomes quite useful, right? So if some of you came down to our Freshers Week stand, you might have seen a problem that we had there where you had a picture frame with 2 hooks, and we wanted to, hang the picture frame in a way such that if we remove one of the 2 hooks, the picture frame will fall, no matter what, no matter which pin you take out, in some way it's going to fall. And turns out the way to solve this, right, is using group theory. So thanks to Georgia, we have had a small introduction. So in fact, we can we've got a definition of the group, more or less. So we've got, for example, for one pin, each pin defines a generator of the group. And we can define this like small a going clockwise like this around the generator. Capital A going like this anti-clockwise around the generator. So then AB would look something like this going over the hoop, right? Small AB, you're going clockwise around one and anti-clockwise around the other. So then ABA here this was actually a popular attempt at this problem. So what happens here? So a lot of people, they said, okay, let's put it over one like this and round the other like this. So what happens here? If we remove one of these, this is akin to removing one of the ones in the equation. So in this case, we're removing the A's here. So we just remove the A's completely out of it, and we get B left over in this equation. If we were to do this the other way, so one thing to note is A and capital A are inverses of each other, right? So let me show that quickly. If you were to go like this around A, and then you go A around that way, you end up, well, this is homeomorphic to that, right? So this is homeomorphic to that with the pin outside, right? In fact, it's over here, right? So removing this one here would be removing would be removing B in this case, and we'd get A times A, which gives us the identity of this group. And anyway, the whole point of this exercise then is to figure out an expression like this, right? Like A, capital B, such that if you were to remove either one of these, so in this case, let's say we remove the A pin, we end up with small b, which gives us the identity. Or similarly, if we remove the B pin, we'd end up with small a, and we'd get the identity again. And in fact, this is then, generalizable to other spaces with more pins, right? So here we can, if we were to remove 2 pins, we can remove B and C, we'd get AA again, and we'd get, the identity of this group. So this is like, a neat example, and the rigorous proof of this comes from something we'll do in a moment. This is a neat example of how algebra comes into topology like this, right? So algebraic topology can be split up into different areas. So there's the study of homotopy theory, which I'll talk about in a moment. There's homology and cohomology, which Luke's not here, but he gave a talk on this recently, last September, I think. And he went, it's all about counting the number of holes in topology space. It's quite nice, you get stuff like the Ram's theorem and Stokes theorem out of it. So it's quite a beautiful area of topology. Then you have topological aspects of manifolds. So manifolds are structures that there's structures that are used in differential geometry and in a lot of different areas of physics these days as well. and they have their topological aspects, which algebra tends to help out with here. And then there's knot theory. So knot theory is an area that, well, as it described, it's knots, right? So what is a knot? A knot is an object like this, right? So you have like a string of some sort that intersects with its, overlaps itself a couple of times, something like that, for an example. And is it possible to untie this knot in some sense and get just a regular hoop like that? Anyway, knot theory tries to understand these things and tries to describe these things algebraically and using topology as well. So yeah. So homotopy. Homotopy is a very interesting area of algebraic topology. So it starts with this definition, right? So we say that two mappings between topological spaces is homotopic if we can continuously deform one into another. So rigorously, that means that we can define another function that is, across the interval here, such that, at one end of the interval, it's the first function, at the other end, it's the second function. But, this is a little complicated just to read. So let's look at it in the picture, right? So all this means is that you can kind of draw a video of the function transforming from one curve into another, continuously. There's a bit of a jump in this video, but it's the fault of the video. So you can get any curve in 2D flat space, right? You can kind of do this. I hope you can see, like, you can kind of get this sort of movie picture going on, so that you can continuously deform one into the other. This isn't necessarily the case with every surface, right? So if we look at the torus, for an example, we can have a curve going around the hole like this, right, of the torus, or one going, around its breadth, right? And you wouldn't be able to continuously deform one into another. You'd have to break one of the curves at one point or another to get through it. So yeah, that's more or less what homotopy is. And then this leads to something known as the fundamental group of topological space. So pick a point in your space, right? Start at that point and consider all of the possible curves that start and end at that point, right, on your space. So for an example here, we've got the sphere, which, you can see a couple of different examples of curves that start and end at that point. Now, take that set of curves, right, and divide it up into the equivalence classes based on homotopy. So you kind of equate all of those that can be continuously deformed from one into another into each other, right? And from that you get that forms a group. I'm not going to prove it rigorously. It's a bit long for that, but it will form a group, and you can see that, for an example, for the sphere, you get the trivial group, which is just the trivial group is just a set that contains the identity element under some operation. So whatever curve you get, it's they're equivalent to each other in this case. And if we have a look at the torus again here, if we were to consider a point here, let me draw some curves. So we could draw a curve like this, right, around the thing, around the hole, and a curve like this around the breadth of it. And these two wouldn't be, obviously, as I said before, they won't be continuously deformed into one another, but you'd be able to equate all the curves that go, like, for example, under the curve like that and back to the point. So that's more or less what the fundamental group is. The fundamental group is it's a group under composition of functions. So a composition of curves. So you start at one curve and you end at the other. So that's all for now from my talk. Feel free to ask any questions if you have any questions. So